In this video, we extend the idea of atomic orbital diagrams for the one electron case of the hydrogen atom to include all other multi-electron atoms, and we also use these diagrams to assist in constructing electron configurations, which are shorthand notations for describing the way in which electrons are distributed around a nucleus. So just to quickly recap, this is the orbital energy diagram for the hydrogen atom that we were introduced to earlier. Remember that in this representation, an orbital, which is just a region of space, is represented by a horizontal straight line, and the characteristics of each orbital can be described using the three quantum numbers n, describing the overall energy of an orbital, L, describing the overall shape of an orbital, and it takes on the letter designations as well for SPD, for L equals 1, L equals 2, L equals 3. And the third quantum number, ML, which sits under the horizontal line here, and I've only represented the 7 orbitals for the 4F subshell here, but all of those other numbers under the horizontal lines actually represent that third quantum number, ML, the magnetic quantum number. Now there is one orbital and one subshell in the n equals 1 shell. There are 4 orbitals and 2 subshells in the n equals 2 shell. 9 orbitals in total in 3 subshells in the n equals 3 shell. And a total of 16 orbitals grouped into 4 subshells at the n equals 4 shell. And finally, we say that the single electron in the hydrogen atom resides in or occupies the lowest energy orbital in this diagram, and we can represent that by placing an arrow in that 1s orbital at the n equals 1 level. Now for multi-electron atoms, as we get more and more electrons in atoms, the electrons are forced into higher and higher energy levels, and it turns out that orbitals can only accommodate a maximum of 2 electrons. And again, if we consider that an orbital is just a region of space, we can explain this using classical physics by acknowledging that it simply becomes more and more difficult to squash multiple electrons into the same small region of space close to the nucleus, particularly when these electrons all have a negative charge and tend to want to repel each other. So that when we get up to element number 3, lithium, one of its 3 electrons actually needs to go into an orbital in the n equals 2 shell, and the same goes for beryllium and boron and carbon, numbers 3, 4 and 5. By the time we get up to number 11, sodium, and even higher numbered elements, we need to start putting the electrons into orbitals at these higher energy levels. Now the shape and orientation of orbitals for multi-electron atoms are the same as those for the hydrogen atom, and the major difference lies in the relative energies of the subshells within a particular shell. So what I mean by that is the energies of the orbitals in the p subshells are slightly raised relative to the energy of the s subshells, and the energy of the d subshell orbitals are slightly raised relative to those in the p subshell. And finally, the energy of the orbitals in f subshells are slightly raised relative to those in the d subshells. Now, this is largely due to electron-electron repulsions when we have more than one electron present in an atom. In multi-electron atoms, the outer electrons experience coulombic repulsion from the inner or core electrons, and this means that the coulombic attraction to the positive nucleus is less than it otherwise would be in the absence of those inner electrons. In other words, they are less restrained by the attraction of the positive nucleus than would be the case in the absence of the inner or core electrons, and the outer electrons are said to be shielded and therefore have a higher energy. Now we can explain this in a little more detail if we use the size, shape and energy of the p orbitals as an example. So the 3 p orbitals of the 2p subshell are represented here in 2 ways. On the right hand side it's represented pictorially in terms of the shape of electron distribution, and on the left hand side in terms of their energies relative to other subshells. Now in reality, these 3p orbitals overlap the same region of space and around the nucleus, and they can be better represented spatially by this diagram at the bottom, where we see the 3 overlapping 2p orbitals. Now, in a multi-electron atom such as nitrogen, for example, which has 7 electrons in its electron cloud, the reality is that 2 of those electrons would exist in the 1s orbital, and we can represent that by placing 2 arrows in that 1s subshell or 1s orbital in the n equals 1 shell. There would be 2 electrons in the 2s orbital, and we can represent those 2 electrons by placing them in the 2s orbital there. And then there would be 3 electrons spread across each of the 3 2p orbitals, representing a total of 7 electrons. Now, because electrons in the p orbitals tend to, on average, spend more time farther from the nucleus than the corresponding electrons in the 2s orbital, the electrons in the p orbital are said to be shielded and therefore are at a higher energy. And that's why the orbitals in the 2p subshell are slightly higher or raised relative to the orbital in the 2s subshell. So the result is an orbital diagram of energy levels like the one illustrated here, and this differs from the single atom hydrogen case, which had all orbitals within a given shell, that is with a given n value, at the same energy level. Now, an interesting feature of the orbital diagram shown here is that the energy of the 4s, so we've got an orbital at the n equals 4 shell, is actually lower than the energy of the 3d orbitals, or the energy of the 3d subshell, and the shielding of electrons in the 4d orbitals happens to such a great extent that the energy of these orbitals is raised higher than the 4s orbitals, whose electron in that spherical distribution actually experience less shielding. Now, to complete the picture of electronic structure of atoms, we need to consider a 4th quantum number. The electron spin quantum number describes the spin orientation of an electron, and it can be shown that in the presence of a magnetic field, electrons behave as tiny spinning magnets with their own magnetic field. Electrons that pass through a magnetic field are either attracted to the north pole of the field or to the south pole of the field, as if they were tiny electrical charges spinning on their own axes, generating their own magnetic field. Now, given that there are only 2 possible outcomes, the spin characteristics of electrons are quantized, with half of all electrons said to have a positive spin and half of all electrons in atoms said to have negative spin. So the 2 spin orientations are therefore assigned quantum number values of ms equals plus a half, and these electrons are known as alpha electrons, and they're denoted by an arrow pointing upwards, and ms equals minus a half, which are known as beta electrons and denoted with the arrow pointing downwards. So we have positive spin or negative spin, spin up, spin down, ms plus a half, ms minus a half is some of the language that we use around this 4th quantum number. So we now know that an electron within an atom has 4 quantum numbers associated with it, and these quantum numbers help us gain an understanding of the electronic structure of that atom and therefore of the chemical and physical properties of that atom. The first 3 quantum numbers give information about the orbital that is occupied by an electron. And the principal quantum number n gives information about the overall energy of electrons in orbitals. The secondary quantum number L gives information about the shape of the electron distribution within an orbital. And the third quantum number, ML, the magnetic quantum number, gives information about the orientation of that electron distribution in space around the nucleus. And now we have a 4th quantum number, MS, magnetic spin quantum number, which gives information about the spin characteristics of electrons. Now it turns out that each electron in an atom has a unique set of quantum numbers. In other words, no two electrons within an atom can have the same four quantum numbers, and this is known as the Pauli exclusion principle and was first postulated by the Austrian physicist Wolfgang Pauli in 1925, leading to a Nobel Prize in Physics in 1945. Now, the Pauli exclusion principle actually restricts the number of electrons in any orbital to 2, and it's the Pauli exclusion principle is the reason why only 2 electrons can fit in any single orbital. And those 2 electrons must have opposite spin. Their spins must be paired, must be one spin up and one spin down. Now the reason for this is that for any given orbital, the values of n, l and ml are fixed, and that since ms, the fourth quantum number, can only take on 2 values, ms plus a half or ms minus a half, then you can only put 2 electrons into an orbital. One must be spin up, one must be spin down. If you try and put a third electron in there, you'll actually be breaking the Pauli exclusion principle. So let's have a look at the implications of the Pauli exclusion principle when we consider the orbital diagram for helium. Now, helium has 2 electrons in its electron cloud, making it the simplest of all the multi-electron atoms. And what we're considering here is the lowest energy arrangement of electrons in helium, not a situation where one or more of the electrons may have been excited into higher energy levels. In other words, we're considering the ground state electron arrangement. Now we can put the first of the 2 electrons of the helium atom in the lowest energy 1s orbital. And we can use this diagram to identify the 4 quantum numbers associated with that electron. For example, the electron exists in the n equals 1 shell, so the principal quantum number n equals 1. At the top of the screen we can see that this electron resides in an s orbital, which corresponds to L equals 0. So the secondary quantum number L equals 0. There is only one possible orientation for a orbital in a L equals 0 subshell, and that is a spherical distribution. There's only one orientation of a sphere, and so ml can only take on one possible value, and that ml value happens to equal 0, the number under the horizontal line here. And the fourth quantum number, we can see that we're representing this in this particular case with spin up, so ms would be plus a half in this case. Now I can place the second electron that exists in the helium cloud into that orbital, and I can place it with its spin paralleled so that both electrons now have spin up. But if I do that, what we recognize is that those 2 electrons now have the same 4 quantum numbers, and that would be breaking the Pauli exclusion principle, so we can't actually do that. What I need to do is to turn that electron upside down, if you like, and have their spins paired, because what I've got the situation now is n still equals 1, L still equals 0, ml equals 0, but now the spin is spin down, so ms equals minus a half, and both electrons now have a unique set of 4 quantum numbers. So let's go to lithium, Z equals 3, atomic number 3, therefore there's 3 electrons in the electron cloud, and again we're considering the lowest energy arrangement, or the ground state energy arrangement. So I've got 3 electrons that I need to place into this diagram now. I can place 2 of those 3 electrons in the 1s orbital, in the lowest available energy orbital, and their spins must be paired, one spin up, one spin down. If I try and, they are the 4 quantum numbers associated with both those electrons in that 1s orbital. If I try and place a third electron into that orbital, what we see here now is these 2 electrons having the same set of 4 quantum numbers, and we can't have that. And so what has to happen now is the third of those electrons actually needs to go up into the next highest available energy orbital, and that is that 2s orbital there. And what we see now is that that electron resides at the n equals 2 shell, so the principal quantum number is 2. L is equal to 0, ml equals 0, ms equals plus a half for that particular electron, and all 3 electrons now have a unique set of quantum numbers. So we're not breaking the Pauli exclusion principle. Now we're going to consider the electron configuration for lithium. Now an electron configuration is a shorthand way of representing the information that's on this orbital diagram. And what we note is that there are 2 electrons that are paired in the 1s orbital, or the 1s subshell. There are there is one electron in the 2s orbital or in the 2s subshell. And so we can write down a shorthand notation electron configuration like this: 1s2, 2s1, where this 2 superscript actually represents the 2 electrons in the 1s subshell there, and this 1 superscript actually represents the 1 electron that's in the 2s subshell. So we get a shorthand representation of the information that's in this orbital diagram. So let's go to atomic number 4, beryllium, which has 4 electrons in its electron cloud. And we can place 2 of those 4 electrons in the lowest available energy orbital, and then we place the next 2 in that 2s orbital, again with spin pair. So if we look at the ground state electron configuration for beryllium, we see that we've got 2 electrons paired in the 1s subshell, or 1s orbital, and we have 2 electrons paired in the 2s subshell. And so we can write an electron configuration 1s2, 2s2 in this case. And again, that 2 superscript indicating the 2 electrons in the 1s subshell, and that 2 superscript indicating the 2 electrons in the 2s subshell. So again, 1s2, 2s2 representing a shorthand notation of the information in this orbital diagram. We can go to boron, atomic number 5, with 5 electrons in its electron cloud. Put 2 electrons paired in the lowest energy orbital, 2 electrons paired in the next lowest energy orbital, and then the 5th electron has to go into this p subshell. It has to go into one of the orbitals within the p subshell. Remember, a subshell is just a group of orbitals. So we can write out a electron configuration for boron by noting that there are 2 electrons paired in the 1s subshell, 2 electrons paired in the 2s subshell, and we've got 1 electron in that 2p subshell. And we can write an electron configuration now: 1s2, 2s2, 2p1. Again, that superscript there representing the 2 electrons in the 1s subshell, that superscript there representing the 2 electrons in the 2s subshell, and this superscript here representing the fact that there's 1 electron in that 2p subshell. So we can keep building up orbital diagrams and ground state electron configurations by successively filling orbitals in a specific order. And that order, as we've seen, is principally governed by filling the lowest energy orbitals first. No more than 2 electrons can exist in a single orbital. That's a result of the Pauli exclusion principles, and the spins of those electrons must be paired. We must have 1 spin up, 1 spin down. Now, for orbitals in the same subshell and therefore having the same energy, we have to follow a rule called Hund's rule. And Hund's rule says that the lowest energy arrangement of electrons in a subshell is obtained by placing electrons into separate orbitals of the subshell first, with the same spin, before pairing the electrons. So what does that actually mean? Well, let's go up one more and let's consider the orbital diagram for carbon. This is atomic number 6, therefore 6 electrons in the electron cloud. I place 2 electrons in the lowest energy orbital, spins paired. 2 electrons in the next lowest orbital, spins paired. I place a 5th electron in the 2p subshell. Now I could place the 6th electron spin paired in the same orbital. Now I'm allowed to do this. It's not breaking the Pauli exclusion principle. However, it is not the lowest energy arrangement. It is not the ground state. Hund's rule says that to have the lowest energy arrangement, I must put the electron in a separate orbital within that subshell and have the spins parallel. In other words, have them both spin up or both spin down. And it doesn't matter which way, but they have to both be the same. Now the ground state electron configuration for carbon we can therefore write out. We see that there are 2 electrons paired in the 1s subshell, 2 electrons paired in the 2s subshell, and we've got 2 electrons in the 2p subshell, and those spins are parallel, meaning that they're both, in this case, spin up. So the electron configuration for carbon, 1s2, 2s2, 2p2. And again, that 2 there representing the 2 electrons in the 1s subshell, that 2 superscript representing the 2 electrons in the 2s subshell, and that 2 superscript representing the 2 electrons in that 2p subshell. So there we have the orbital diagram and electron configuration for carbon, and we can keep going up the periodic table and add a 7th electron, for example. That's what the orbital diagram looks like, and we're obviously talking about nitrogen here, atomic number 7, and its electron configuration now being 1s2, 2s2, 2p3. There are now 3 electrons in that 2p subshell. Add an 8th electron, so we have to now go over and start pairing the spins, and that 8th electron results in an electron configuration for oxygen, Z equals 8, or atomic number 8, 1s2, 2s2, 2p4. Add a 9th electron, we need to start pairing it up in that middle orbital there, and we're talking about fluorine, 1s2, 2s2, 2p5. There are now 5 electrons in that p subshell, and we can complete filling up that subshell by going to adding a 10th electron that gets paired in that 3rd orbital there, and we're talking about neon, atomic number 10, 1s2, 2s2, 2p6. So just a reminder again, can't overemphasize this point enough, those 2 electrons there representing the 2 electrons in the 1s subshell, those 2 electrons representing the 2 electrons in the 2s subshell, and those 6 electrons representing all those 6 electrons in the 2p subshell. And what we see here is that when we sum the superscripts, 2 plus 2 plus 6, that equals the total number of electrons, in this case for neon, which equals 10. So knowing how to write electron configurations becomes important later for understanding chemical bonding, as well as other trends in the chemical and physical properties of elements and atoms. In follow-up videos, we will see how to generate electron configurations for any atom in the periodic table, including those with many, many more electrons, and we will also see how some anomalous electron configurations arise, which are exceptions to the general rules introduced here.